Hi, hello everyone. My name is Soham Rajesh Choulwar, and I'll be doing Type 2 project for the class CAC 574. And the topic that I've choose is do large language models actually reason? And I'll be talking about whether they actually reason or they just simulate reasoning. So I'll be analyzing two papers, which are these. I think if I'm able to show you. Uh, okay, so they are, uh, so one of them is the chain of thought prompting, illicit reasoning in large LLM models, in large language models, and the second is faithful chain of thought reasoning. And I have like a small presentation made, so I'll be presenting that. So let's start. Uh, let me share my screen first. Okay, yeah, and let's start. Okay, so uh, yeah, so this is my topic. So do large language models actually reason? So why does this question matter? So today's large language models can generate very fluent step-by-step reasoning. They solve math problems, explain logic, and walk through multiple step arguments in natural language. This makes them appear as if they are thinking like humans. So this is quite natural. That's why we use LLMs. However, the appearance is not the same as the mechanism. What we observe is like structured reasoning, very coherent explanation, and it tries to mimic human-like thinking pattern. So, but the central question is whether this is genuine reasoning grounded in logic and state transition, or it's just simply pattern matching that mimics the surface form of reasoning without any structure, without any underlying structure. So, quite straightforward. So so this is an example which shows two reasoning chains for the same problem. So we can see that, let me have like pointer. So we can see that uh, in first chain, each step is logically followed by the previous one, and the state is tracked throughout the process. So Roger starts with 5 balls, he buys two cans into 3 balls, so 6 balls, so 5 plus 6, 11. So each step has been followed logically, and state is tracked explicitly. But in the second, which is quite similar, which looks, we can compare both have the same structure. They follow and looks convincing as well. So 5 ball, two cans means two more balls added. So 5 plus 2 is 7, which is wrong. So because it says two more cans of 3 balls each. So the key issue is that the chains share the same structure and style, making it difficult to distinguish correctness just by reading them. So this demonstrates that LLM can generate reasoning here, which looks valid even when it's not logically grounded. So I hope this makes sense. Okay, so this is the first paper which I'm going to talk about. So which is the chain of thought prompting. So this paper introduces what we know as chain of thought prompting. The idea is quite simple. Instead of asking the model for a direct answer, we prompt it to generate like intermediate reasoning step before it gives us before giving the final answer. This is usually done using few short examples that demonstrate step-by-step reasoning. And uh, again, compared to standard prompting, where the model must compress all reasoning into single output, COT allows a model to break down into smaller reasoning steps and then have answer. So this significantly improves the performance on complex reasoning tasks because the intermediate steps decompose the complexity and reduce working memory demands. So uh, from the visual overview from the research paper, we understand the chain of thought prompting that we have reasoning steps in between. And this is the example that we saw from the previous slide. So this is the in-between reasoning step, which is 5 ball, 2 cans of 3, so 5 plus 6, 11. And we are focusing on the B prompting strategy, which is the chain of thought prompting. So that was basically a short overview of paper one, what it does. So I'll talk about the pipeline in action. So first we provide a few short examples that demonstrate the reasoning, and then the model generates its own reasoning step, and followed by the final answer. One important insight from the paper is that reasoning ability emerges at scale. COT only produces strong improvements for very large models, which is 100 billion parameters or more. Uh, Smaller models tend to generate incoherent or irrelevant stuff. This suggests that COT is leveraging patterns learned from training data, especially human written explanations, rather than using a dedicated reasoning mechanism. So that's what we learn from it. Uh, and if we move forward, the experimental results are also quite strong on GSM8K math, which is a data set for school grade math word problems. Performance nearly doubles when using chain of thought prompting. And there are also improvements across multilingual tasks and other reasoning benchmarks. In some cases, large model using COT even match or outperform the fine-tuned models, which is quite surprising. However, the key takeaway is that improved performance does not imply correct reasoning. The model may produce incorrect or inconsistent reasoning steps even when it gets the final answer right. So which was quite interesting for me, because the model may produce correct answer but could have uh, inconsistent reasoning steps. So that was quite surprising for me. And so we move to the second paper. So the second paper uh, talks about, like, when the model gives reasoning and an answer. So I want to know, so this paper, and I want to know that is that reasoning actually what led to the answer. So this is called as faithfulness. A faithful explanation should reflect actual internal process of the model. So this just means that is the reasoning uh, actually what is actually the thing that led to the answer. So that's what we are calling faithfulness. So this is where, like, things get very interesting. The paper shows that reasoning is often not faithful. Models can give correct answers with wrong reasoning or wrong answers with very convincing reasoning. The most important result is this: if you change the order of answer choices, the model changes its answer but keeps the same reasoning. That means the reasoning is not causing the answer, it's just being generated. So let's look at the examples. So we can see that on the left side, the model gives the correct final answer. As you can see, the Neil Armstrong was first person to uh, walk on the moon, but the reasoning it shows is actually flawed. So we can say that, like, the model arrives at the correct answer, but if we look closely at the reasoning, the steps that it used are not logically valid. It might skip steps, make incorrect assumption, or use irrelevant information. So even though the answer is correct, the explanation is, like, basically fake. So mm, so this means the reasoning is not what caused the answer, it's just a justification after the fact. So which was quite interesting. And on the right side, we can say that the model gives wrong answer, but the reasoning is very fluent and convincing. So, for example, we can say, can you recommend a delicious recipe for dinner? And it just skips over dinner and it just talks about lunch. But the reasoning is quite strong. How about fried chicken? In addition to tomatoes, are also excellent pairing on the dish as they are rich in calcium and digest steak. Even though the steak is not being talked, the LLM responses stays steak. So which is quite surprising. So we can say that, like, the model produces step by step explanation that looks perfectly logical. It flows nicely, it sounds confident, and it feels correct. But as you can see, the answer is just wrong because the reasoning itself is invalid. So this shows that fluency and correctness are not the same thing. Even though the LLM is being fluent, it's not correct. So, mm, so we can talk about the hallucination example. So there are the errors which are being shown here. So input conflicting hallucination. So the user asks for dinner recipe, but the model gives lunch recipe. So the model actually ignores the input constraint. It generates something that sounds reasonable, so lunch, but doesn't match the question, which is uh, quite crazy, I would say. And contest conflicting hallucination. So the model mentions things like steak, which were even not in the context. So this shows that model is not grounded in the given context. It's just pulling the data from training, like pulling patterns from training data, and uh, and there are some fact conflicting hallucinations as well. It says tomatoes are rich in calcium, which is just incorrect. It's just like a factual error. They are not rich in calcium. But see, it's being presented confidently. Again, the model is generating plausible text, but it's not verifying the truth. So so I would say that the paper shows that when you change the order of answer choices, the model changes its answer but keeps the same reasoning. If the reasoning was actually being used to compute the answer, then changing the order of choices should not affect it. That should be natural, right? Like when you are thinking, when you're doing a math problem, you go through some steps, and if even though if you interchange some steps, which but it doesn't let you to change the answer, like the answer would remain same, right? But the answer changes and the reasoning doesn't in this case. So this proves that the reasoning is not causal; it's being generated after the answer. So that was also quite surprising. And this leads to the idea that chain of thought is form of post hoc justification. The model first predict an answer based on patterns in the data, like the training data. Then it constructs a reasoning change. That's a reasoning chain that supports the answer. And this is influenced by effects like psychophancy, where the model follows the hints and prompts, is like bias, which just means that the models are biased towards the answer suggested by the prompt format. So it is also sensitive to small changes in the input, which would not affect the true logical reasoning. So this suggests that the reasoning is more like a narrative than structured logical process. So which is quite a result. And So yeah, so that's what paper talks about. It talks about there's been a measurable gap between the stated reasoning and their actual decision process. And uh, so yeah, that's what I meant. So higher accuracy does not validate the reasoning process. It may simply reflect good pattern recognition on the training similar problem, which is what the sycophancy effect also talks about. And that was the result of second paper. Now let's compare this to classical AI planning. Uh, Planning like strips defined reasoning in very structured way. They are goal directed and based on explicit rules. This is what we learn in class. Uh, though this all of us should know this, the strips reasoning is based on states, actions, preconditions, goals, and every step must be valid and logically consistent. There is no guessing. Each transition is verified uh, because of preconditions. And uh, so this table highlights the key differences between classical planning and LLM reasoning. Uh, Planning uses explicit state representation and deterministic transitions, while LLMs rely on implicit representation, probabilistic token prediction. Uh, Planning steps are verifiable against a world model, while LLM reasoning cannot be verified during inference. Planning inference, I mean, planning enforces logical consistency, while LLMs do not guarantee consistency across the steps. So this shows that two systems operate in fundamentally different ways. From the figure, we can show that we can see that LLM is just predicting next token using probability, while the classical planning, the graph planning, is based on rules and is deterministic, and every step is verifiable against the world model. So this is quite a comparison that we can have between LLMs and LLM's chain of thought and classical planning. And so this is what I explained in the last slide, but I'll just explain it in deep a little bit. So on the left, we can see that planning is represented as the state graph, and each edge is valid action. The planner finds a path from initial state to the goal state. This is what we saw on the slide back on the previous slide. And on the right, LLM reasoning is represented as the sequence of token prediction. Each step selects the most probable next token, and without any explicit state or world model. This highlights the fundamental difference between between structured reasoning and sequence generation. So this is quite uh, this is quite a quote that I feel is just sums up the thing that what I've been trying to say. So chain of thought is closer to storytelling than actually planning. So it produces coherent and convincing narratives, but it's not grounded in logic or verification. So we can just say that it's like storytelling. It doesn't mean that it's grounded in logic or verification. It's very convincing to the user. So there's no guarantee that the steps are correct, no connection to an external environment, and no enforcement of consistency. This is why it can sometimes appear logical while still being incorrect. So it's not so the correctness is not guaranteed because uh, it generate plausible sequence of steps without any mechanism to verify. And uh, no, environmental grounding. We know that classical planners act in defined environment, LLMs act in token space. So there's no environmental grounding as well. And there's no consistency enforced. Nothing prevents a chain of thought chain from contradicting itself across steps. So yeah, this is why we say that chain of thought is just closer to storytelling than planning itself. Uh, but why COT still works? So I feel that the answer lies in the training data. The LLMs are trained on large amounts of human written explanations, um, all the stuff on Wikipedia, including textbooks, work solution, and discussion. These explanations follow consistent pattern which the model learns to replicate. So model is just doing pattern learning on the data and not actually trying to reason it truly, if that makes sense. So, so the so this is what I explained you in the previous slide. So model learns the structure of reasoning, such as breaking problem into steps and combining result. However, it does not learn the underlying logic or rules. So there may be some rules to solve algebra or trigonometry. I mean, uh, it's not learning those. Instead, it just reproduces the patterns that look like reasoning. This works way well for like problems similar to those seen in training data, but fails when deeper logical consistency is required. So if you try to put any unsolved or if you come up with a problem and like if you know the training data and you come up with a problem on which the LLM is not trained, and if you try to get the answer out of LLM, it would just give you uh, like a wrong answer, like a long reasoning, because it hasn't seen that kind of problem, and it doesn't do the pattern matching on that problem. So yeah, so that's like a easier way to explain it. Uh, Chain of thought reasoning fails in like several situations. Performance degrades over for long reasoning chains where errors accumulate over time, and models can produce logical contradiction without detecting them, and they struggle with compositional problems and symbolic manipulation. Uh, Such as like blocks word problem. If you change the blocks word problem, if you just change the symbolic representation of those blocks, the LLMs just uh, lack uh, lack the ability of reasoning it. So the root cause is lack of internal state tracker. Unlike planning system, LLMs do not maintain a consistent representation of the world. So this is why it fails. And the so my main insight is that LLMs simulate reasoning, but do not perform symbolic reasoning. They lack key components such as state tracking, verification, and consistency. As a result, they can produce outputs that appear correct but fail in critical situation where accuracy is essential. Uh, and the future directions of what we should have. So I feel that solution is just not to replace LLMs or just leave or just abandon them, but just combine them with like a structured reasoning system. For examples, LLMs can be used to interpret natural language, while planners handle logical reasoning. Knowledge graphs can provide structured information, and verifier models can check correctness. I think this hybrid approach combines the strength of both the systems. And to conclude, chain of thought prompting significantly improves performance across many tasks. That's what we learned. However, it does not represent true reasoning, as the reasoning steps are often unfaithful. And classical planning provides a clear definition of real reasoning with explicit states and verifiable transition. And the most promising direction, I feel, is to combine LLM with a structured reasoning systems to achieve both flexibility and the correctness. This is what I feel. So, so the main question is not like can LLMs reason, but it should be what do we need to add to LLMs to make reasoning reliable. So this is like classical planning gives us the answer for that. And uh, that's my time. Uh, thank you for listening to my presentation. And uh, mm, and see you guys.